You're welcome to today's class. I want to believe you guys are doing fine today. This is Chemistry Hangout. If you are just watching this YouTube channel for the very first time, kindly subscribe to this channel and turn on the notification bell so that when we upload any video, you are going to be notified. Today, very important, very quickly, we are going to be considering another wonderful gas law in chemistry, and we refer to it as Dalton Law of partial pressure. Dalton law of partial pressure. This is another wonderful law in chemistry, and I want you to pay maximum attention as I break down this very particular, law, and I will solve a lot of questions to give us confidence, to build confidence on this very particular topic. So, what is Dalton law of partial pressure? What is the law? Let's get the law stated. Let's state the law. Then we can now explain what the law is talking about. This law states that this law, so pay attention, this law states that Dalton law of partial pressure states that in a mixture, okay, in a mixture of gases which do not react chemically together, I hope you are following. Please pay maximum attention. This law states that in a mixture of gases which do not react chemically together, the total, let me put a comma, the total pressure of a mixture of the mixture of the gases is equal to the sum of the partial pressure pressure of the constituent gases of the constituent gases. Now, what is this law saying? What is the meaning of this law? What can we infer? What can we actually, understand from this law? The law states that in a mixture of gases which do not chemically react together or who do not react chemically together, the total pressure of the mixture of the gases is equal to the sum of the partial pressure of the gases. The total pressure of the mixture of the gases is equal to the sum of of the partial pressure of the gases. Let's take examples. I want us to get this law. I just want us to understand this law. So let's take, for example, I have a container like this. I have 3 containers. I have another one. In this place, I have gas A. Okay. In this place, I have gas B. And in this place, I have gas C. Because these are gases, okay, they will actually exert a pressure in this very particular vessel. These are the vessel. They will exert pressure here. Are we together now? They will exert. C, we have its own pressure, which is its partial pressure. B, we have its own pressure, which is its partial pressure. A2, we have its own pressure. Do you understand? Now, if I now look for a big vessel, okay, pouring gas A inside, gas B inside, and gas C inside. So this is gas A now, this is gas B, and this is gas C. I want to believe this is clear. The law is now saying that in as much as these 3 gases do not react together, let's say the partial pressure of this one exert a pressure here, let's say 20 millimeter mercury. Okay, this one exert a pressure, let's say 30 millimeter mercury, and this one exert a pressure, let's say 40 millimeter mercury, right? Now the law is now saying if I put them in another container, okay, in as much as they do not react together, the total pressure that I will have here, don't forget that for A we have 20 millimeter mercury, for B we have 30, and for this we have 40. So the law is now saying that the total pressure I will have in this big container will be what? Will be the sum of the partial pressure of this. You understand that now? So which means if I want to have my total pressure, which is the PT, will now be the partial pressure of gas A plus the pressure of gas B plus gas C. Can you see that now? So which means if I want to determine the total pressure in that cylinder, it's going to be 20 millimeter mercury plus 30 millimeter mercury plus what? 40 millimeter mercury, and that will give me what? That will give me 90 millimeter mercury. I hope this is clear. That's just what the law is actually saying. That's what the law is saying, that if two or more gases react together, their partial pressure, in as much as they do not react chemically together, the total pressure you are going to have will be the sum of the partial pressure of the constituent gases. So take note of that. So we can now say that mathematically, if you want to represent that law mathematically, we can say that the total pressure in this container, I use this as a case study. I use this VSO as a case study. Now the total pressure here will be pressure of in gas A plus pressure in gas B plus the pressure in gas C. And this very particular illustration is the Dalton law of partial pressure. So where your PT is the total pressure, while your PA is the partial pressure of A, your PB is partial pressure of B, while your PC will be the partial pressure of C. I want to believe this is very, very clear. Okay, I want to believe this is very, very clear. So if we want to calculate this quantitatively, let's move on. I want to believe that example is clear now. So if we want to quantitatively, if I want to calculate my total quantitatively, if I want to get my if I want to get my, if they ask me to get my partial pressure, because here in that example, they didn't give us the partial pressure of this. We are assuming that we know it, okay? So if we want to calculate the partial pressure, okay, if we want to get our partial pressure, if there is a need for us to actually calculate it, it's going to be our mole fraction. We are going to take examples, so just calm down. A mole fraction of gas times the total pressure. So in a scenario where we are asked to get, if we want to get our total pressure now, we can always add the partial pressure of A, the partial pressure of B, the partial pressure of C. Understand? But in a scenario where we don't even know the partial pressure of A and we are given the total pressure, we can use this very particular formula. Please take note of this. I'm going to apply it so that you see the way. So I can use this formula to get my partial pressure. So take note of that. Very, very important. Take note of that. Let's take examples to buttress this Dalton law of partial pressure. Let's take example one, just like 3, 4, or 2 examples, and it will be crystal clear. So note this. Let me just put so that you can see the PT and the formula for calculating partial pressure. Okay, so we have that example one, that a gaseous mixture, okay, a gaseous mixture containing 64 grams of oxygen, and 70 grams of nitrogen, okay, exerts a total pressure, okay, exert a total pressure of 1.80 atm. That's atmospheric pressure. What is the partial pressure? What is the partial pressure exerted? What is the partial pressure exerted by oxygen in the mixture? Look at this question. Very wonderful question. So how do we go about this? How do we go about this? A gaseous mixture containing 64 grams of oxygen and 70 grams of nitrogen exerts a total pressure of 1.0 atm. What is the partial pressure exerted by oxygen in the mixture? And they gave us the atomic, the weight. Oxygen is 16. This is a very common value that we are always giving, and this is 14. So let's take it one after the other. The first thing here is to get our mole ratio first. We need our, because for us to get a partial pressure, look at that, we need our mole ratio. We are already given the total pressure here. That's 1.80 atm. So we need our mole ratio. So let's get the mole ratio of oxygen. Or let's say the mole. Then we can now look for the ratio. So let's just take the mole of oxygen first. Let me use my eraser here. So let's take the mole of oxygen first. So that one will be clearer so that we will not make mistake. So let's take the mole of oxygen. How do we calculate mole? So we want to calculate mole of oxygen. If you remember in our rudiment chemistry, the formula for calculating mole is mass over molar mass. Okay. So from here now, the mass of oxygen is given in the question to be 64, okay, over molar mass, oxygen gas. They've given us 16 already, so that will be 16 times 2. I want to believe this is clear. So from there, we are going to have 64 over 32. 16 times 2 is 32. So our mole of oxygen, if we divide 64 by 32, it's going to give us 2.0 mole. I want to believe this is clear. So let's look for the moles of nitrogen too here. The moles of nitrogen. Same formula, mass over molar mass. Then in the question, they gave us the mass of nitrogen. That is 7 over nitrogen 2 is a gas. So that will be 14 times 2. And that will give us 7 over 28. And if we divide 7 by 28, let me use my calculator. 7 divide 28. 7 divide 28. That's giving me 0.25 mole. 0.25 moles. I hope we are still together. Okay. Now, don't forget that our formula, let's go back. Our formula is partial pressure, stated earlier. For us to look for partial pressure, the formula is what? Our mole fraction or our mole ratio. You understand? Our mole ratio, mole fraction of the gas, or mole ratio of the gas times our total pressure. The mole fraction of the gas. Very important. So that some people will not make mistake. Let me quickly, because if you are saying mole, okay, that's what you have written, mole fraction of the gas. So we want to see the mole fraction of the gas here now times our total pressure. So now what is the mole fraction now? Let's get the mole fraction. Now, what is the mole fraction? Now, for us to get the mole fraction, we need to get the total mole ratio, right? So, for the mole ratio, that's the total ratio. Let me use NT because mole is, represented by N. So, the total ratio will now be what? The ratio of what? Of oxygen plus the ratio of what? Of nitrogen. And what is the ratio of oxygen? That's 2.0 plus what's the ratio of nitrogen? That's 0. That's, let me see this so that we'll be sure. Oh, sorry, this is 70. not 7, please. This is 70. Okay, this is 70. This is 70. I wrote 7. That's a mistake. Look at this. This is 70, not 7. So let's do 70 divide 28. So 70 divided 28 is 2.5, not 0.25. So take note of that, please. So that's just a mistake. Thank God I saw it. So that's 2.5 now is our value, 2.5. So let's quickly correct that. Let me pick my pen. Okay, let me pick my green pen. Okay, thank God I quickly saw that. So that will be 2.5 moles. 2.5 moles. Okay, so don't let us change the question. So our total mole ratio now, what will now be our total mole ratio now? That will now be what? 2.0 plus 2.5, and that will give us 4.5 moles. I want to believe this is clear. Yeah, I want to believe this is clear. So for our partial pressure now, we can now calculate the partial pressure now of oxygen. The partial pressure of oxygen as stated in the question. You need to go over this over and over again, which is equal to mole fraction. Can you see that? Mole fraction now means what is the partial pressure? Which of the gases are we calculating the partial pressure? Oxygen. And the mole of oxygen is 2.0 over mole fraction means the addition of the two moles. Okay, the mole fraction is the mole we are calculating for that 2.0, then over the total, which is our NT, this one, the total of the two moles, that will be 4.5 times what is the the total pressure as stated in the question. Let's go up. Okay, 1.08 atm. Can you see that? This is it for people that are, this is it, 1.0 atm. Can you see that? So let's go down and infuse that very particular value. So let's infuse that very particular value, 1.0. So this will be 1.80. So from there now, we can now calculate the ratio of oxygen exerted in the mixture. That will be 2 times 1.80, okay, divided by 4.5, and that's giving us is 0.8 atm. Is 0.8 atm. So the partial pressure of oxygen in that very particular mixture is 0.8. Let's say, for example, they ask us to calculate partial pressure of nitrogen. They didn't ask us in the question. I'm just doing it so that we'll understand better. We want to calculate partial pressure of nitrogen. Okay, that will now be what is the mole fraction, what is the mole ratio, or what is the mole of nitrogen? The moles of nitrogen from the question we solved is 2.5 over the total mole ratio, that's 4.5, then times the total pressure, 1.80. Can you see that? So let's see. That's if you are asked to calculate for nitrogen, but we are not asked. I'm just doing that for better understanding. So that will be divide 4.5. Can you see that now? That's 1 atm. Look at that. Look at that. Can you see something? 1 atm. And what is the law saying before? That total pressure will be pressure of A plus pressure of B. Can you see? So pressure of A is 0.8 plus pressure of B, that's 1. And it is giving us 1.8 atm, which is the total pressure given in the question. Which is the total pressure given in the question. So our answer is correct because the law has been proved that A plus B will give us the total pressure. So the partial pressure of A plus the partial pressure of B will give us the partial pressure of what? Will give us the total pressure in the mixture, of the mixture. So that is very, very correct. So they asked us to look for only oxygen though, but I'm just doing nitrogen for better understanding. And I want to believe this is very, very clear. I want to believe this is very, very clear. Let's take example. So I'll just solve around 2 to 3 questions on this very particular one, okay, so that it will be very, very, very clear. So let's take example 2. But one thing about this law is you have to go over the video over and over again for you to actually get this very particular law, that law of partial pressure. But it's very simple. So let's take example 2. So the example 2 says 50 centimeter cube, okay, of a gas X, 50 centimeter cube of a gas X, and 30 centimeter cube of a gas Y, okay, of a gas Y, occupy a container, with a capacity, of 80 centimeter cube. Okay. If the total pressure, if the total pressure, if the total pressure of the gas mixture, the total pressure of the gas mixture is 760 millimeter mercury, is 760 millimeter mercury, right? Calculate the partial pressure, calculate the partial pressure of gas X and Y. Okay, let's look at this very particular question. Let's have this in our mind, very important. You know, we have already established that fact that if we are looking for partial pressure, if you are looking for partial pressure, we stated that already. If you are looking for partial pressure, it will be what? It will be the mole fraction. It will be the mole fraction, okay, of gas times the total pressure. We have established that fact already. So from here, but if you look at this, they didn't give us a value to calculate the mole fraction, but we can get the volume fraction. You understand, of the gas? Because here they are giving us, if you look at the question, they are giving us in volume 50 centimeters instead of them to give us in mass like we did in the first one. Here they are giving us volume. So we are still treating it same way. I want to believe that this is clear. We are still treating it same way. So let's look for the total volume of the container, which will now be representing, which will now be representing the total mole ratio. So the total volume here. So the total volume of container. So the total volume of container, as stated in the question, is 80 centimeter cube, which is just like the total mole, the total mole ratio. Do you understand? Total mole ratio. That's just the meaning of it. Why they gave us the volume of gas S, which is representing the mole of X. Instead of them to give us mole now, they are giving us in volume. That's 50 centimeter cube. I want to believe this is clear. Very, very important now. And the total pressure. What is the total pressure they gave us? 760 millimeter mercury. So we can calculate this. It's a very straightforward question. So we can do something like this now. That the partial pressure of X now, partial pressure of X will be, what is the volume of X, which is representing like the mole of X, because they didn't give us a mole, they gave us in volume. So that will be 50 over, you are supposed to now have the addition of the mole ratio, right? You are supposed to have the addition of the mole ratio, which is now representing like the addition of the volume that they gave us here, which in turn gave them this 80 centimeter cube, because it's just like them adding 50 and 30. So that will give us the total volume that's giving us 80, right? That's the mole fraction of the gas. This is now the volume of the gas now, since we are working with volume, times what is the total pressure. The total pressure as given in the question is 760 millimeter mercury. So that will be 760. So the partial pressure, okay, the partial pressure of X. Now let me use my calculator. That will be 50 times 760 times 50 times 760, okay, divide 80. That's giving me 475 millimeter mercury. That's 475 millimeter mercury. That's the partial pressure of X. Let's move to the partial pressure of what? Of Y. So let's calculate the partial pressure of Y. Don't forget the volume of Y they gave us. Let's see. Volume of Y they gave us, that's 30. Can you see? The volume of Y given to us, is it 30? Can you see that? So let's move down now to solve now for the partial pressure of Y. Okay. Now the partial pressure of Y, look at this now. So the partial pressure of Y will now be, what is the volume of Y that is given in the question? 30 over the total volume, that's 80, times the total pressure, that's 760. So what is our answer giving us? That's 30 times 760. Okay, divide 80, and that's giving us 285 millimeter mercury. 285 millimeter mercury. So the partial pressure of Y is 285. Now, if I want to check if my answer is correct, I already know that the total pressure will be the partial pressure of gas S, right? Plus the partial pressure of gas Y. And look at it. The partial pressure of X is 475 plus the partial pressure of Y is 285. And if you add this together, it's going to give us what? It's going to give us, let's see, 760, okay, millimeter. Can you see that? Which is in line with the total pressure they gave us, meaning our answer is correct. Look at the total pressure they gave us. Look at that, 760. Look at that, 760. Which means after doing the partial pressure of the gases, we are able, if we add them together, you will get the what? The total pressure. Very simple, very interesting. Let's take the last example before we call it today. So if you are just watching this YouTube channel for the very first time, kindly subscribe to this channel. This is one of the best chemistry channel as far as chemistry content is concerned. So you are just watching this YouTube channel for the very first time, this is a place to be. Kindly subscribe and turn on the notification bell so that when I upload any video, you are going to be notified. This is Chemistry Hangout, and for all our Chemistry Hangout family, for people that already are subscribers, oh, thank you for your motivation, thank you for your word of encouragement, thank you for your support so far. We are very, very, very grateful, and we hope to do more on this channel. We hope to do more. We hope to give our best on this channel. So let's see example 3. Two vessels contain separately 50 centimeter cube nitrogen at 100 millimeter mercury pressure and 80 centimeter cube of oxygen, okay, of oxygen at 200 millimeter mercury, at 200 millimeter mercury, and they were connected. Wow, I love the question. And they were connected, by taps. They were connected by taps to a third vessel, containing 30 centimeter cube of hydrogen, at 500 millimeter mercury. I know some persons will be like, wow, this question, what is TAP looking for in the Dalton Law of partial pressure? These are just technical way to actually set the question. They can give us a technical question like this, but don't let us be afraid. We're going to break everything down so that we understand how to solve it. Okay, if the tap are opened and the gases, if the tap are opened and the gases are allowed to mix, until equilibrium is attained. That means until all of them mix together very well. Until equilibrium is attained. Okay? Until equilibrium is attained. And it said determine One, the partial pressure of each of the three gases, of each of the three gases. Okay. Then the second one, they ask us to determine the total pressure. So definitely if you have gotten the partial pressure, you just add everything together to get the total pressure. So the second one is not difficult. Even the first one is not difficult. So we see how we are going to do that now. So, but very important, we have to get the partial pressure of this very particular vessel now. Now look at the question. Two vessels contain separately 50 centimeter cube of nitrogen at 100 millimeter mercury pressure, 80 centimeter cube of oxygen at 200 millimeter mercury, and they were connected by taps to a third vessel containing 30 centimeter cube of hydrogen at 500 millimeter mercury. The first thing you can see, we are solving this question in terms of volume too. Okay, we are solving this question in terms of volume. Very important. Two vessels contain separately. Look at the volume of nitrogen. So let's say solution now, and let's say the total volume. Let's get the total volume. Very important. So they said 50. They said 50 of this coming. Let me write in this so that we can get the question. Well, let's brighten this. Sorry, let's brighten this. Okay. Okay, so let's take the total volume now. The total volume. So they said 50 centimeter cube of nitrogen. So 50 centimeter cube plus 80 centimeter cube of oxygen. Okay, 80 plus they connected it to another one because everything will now be the volume. The volume will all be together. So we have this. Can see 30 centimeter cube. So this is 30 centimeter cube. So if we add everything together, 50 plus 80, that's 130 plus 30, that's 160 centimeter cube. That's the total volume in that vessel because they have added everything together. So in that third vessel, they have added the third vessel to the first to the second. So the total volume there is now going to be 160 centimeters. So very simple now. So we can now take partial pressure of nitrogen. Can take partial pressure of nitrogen, and that will be what is the volume of nitrogen, just like we are taking mole ratio, but they didn't give us in mole ratio, they gave us in volume. So that will be 50 over the total, that's 160 times the pressure that is given. Very, very important. The pressure that is given. Let's look at the pressure here. Let me take this off. Take this off. So if you look at this pressure here, look at the pressure here. You can see the pressure of the first one is given already. Two vessels contain separately 50 centimeter cube nitrogen at 100. So that will be 100. So let me use my calculator to actually get that. So that will be 50 times 100 divide 160. And that's giving me 31.25. So this is giving me, so the partial pressure of nitrogen is 31.25 millimeter mercury. I want to believe this is clear. So from there we can get the partial pressure now of what again? Of oxygen, using same format of oxygen, and oxygen will be what? 80, that's the volume of oxygen, over the total volume, that's 160, times what is the pressure oxygen was actually exerting, that's 200. So this is 200, and that will be what? Use our calculator. 80 times 200, okay, divide 160, and that's 100. That's 100 millimeter mercury. This is 100 millimeter mercury. Why the third one now? The third one, here, if you look at this is operating at 30 centimeter cube and a pressure of what? 500 millimeter mercury. So partial pressure of hydrogen now, of hydrogen, that will be 30, okay, over 160 times what? 500. And that will be what? 30 times 500, okay, divide 160. That's 93.75. Can you see? So we are getting the partial pressure as indicated in the first question, or as asked in the first question. This will be 93.75 millimeter mercury. So we have answered this question. The partial pressure of each of the three gases has been done. Very simple. Very simple. Just understand the procedure. Now they are now asking us to look for the total pressure. So that one is much more easier. So their total pressure, okay, is going to be the partial pressure of what? Of nitrogen gas plus partial pressure of oxygen gas plus partial pressure of hydrogen gas. So their total pressure, that's the PT, total pressure will now be what? Will be 31.25 plus 100 plus 93.75. So let me use my calculator. 31.25 plus 100 plus 93.75, and that's giving me 225 millimeter mercury. So our PT is equal to 225 millimeter mercury, and that is the what? The total pressure. So that is that, guys. That is that. Very simple. Go over this video over and over again. If you need to rewatch this video, do that over and over and over again. Okay, so very, very important. If you are new to this channel, kindly subscribe to the channel and turn on the notification bell so that you would be notified when I upload any video. So if you think you still don't understand this concept, watch it over and over again carefully, religiously, so that you will get this, and lay your hands on questions too. Very important. Lay your hands on some questions on that thing of partial pressure and try to solve them and see if you will get them. So thank you for staying with us today on the channel. Till we meet again on this channel, stay chemically active. I love you guys. Bye bye for now. Thank you. Chemistry Anger.